45 minutes to go. So before the break, what we discussed was sort of how to answer some of the basic questions, how to do some of the basic comparisons, some of the exploratory concepts, how to use PCA and cluster analysis. And one thing that comes, whatever statistical procedure you use, is this issue. So I would like to spend a few minutes, given the fact that this is also something that you may see in the untargeted report. So given the fact that even if you have a targeted platform, a targeted assay, you're still getting a few dozen metabolites, and let alone if you have an untargeted platform where you have hundreds and even possibly thousands of features, then you end up basically doing hundreds of thousands of hypotheses. It doesn't matter whether you do that from a t-test, a simple pairwise comparison, or you build one of these more complicated models that we talked about just before the break. At the end of the day, you have this issue of multiple hypotheses and comparisons, and that means that you need sort of to be cognizant and aware of this issue and take care of it. And there are two key concepts. This is in statistics, the family-wise error rate, and then a more modern approach, especially where you have lots of compounds. So this applies when you have a few compounds. Let's say you do a target assay, maybe 20, 30 hypotheses. But the moment you start going to a large number, especially in an untargeted assay, you need sort of to switch. So these are things that probably you have seen in papers, and people always say, and we controlled FDR, false discovery rate, at a certain threshold. But why is it important? And this is sort of the usual table that we talk about, and I'm paying a particular attention to this box. So in this case, essentially, if you look at what the actual situation is that you don't know, basically here you have that your null hypothesis is true, namely that there were no difference in the mean levels between the two groups for a particular compound, but you say that actually there were differences. So basically this starts inducing false positives, and so you make this type of mistakes. And usually, in most of the cases, and some of the results that come in one column of the report, you get a p-value, and in some of the results sort of that Tanu showed for the lipidomics platform, she said, okay, we detect about 1,200 lipids, and they were differentially expressed a very large number, if I remember correctly, something like 750, by setting the probability of having false positives at 0.05, and therefore there was a lot of those. However, you need to be a little bit careful and trim down the list a bit more, and I think that information is also provided in the untargeted report. And this is something that, especially for those of you that come from genomic data, where you even make more comparisons, we heard before the break, well, usually there are 20,000 genes that may be active. In that case, you do thousands of hypotheses, and therefore this is a very general issue. So what I'm showing here, forget the math, given the fact that it's after lunch, but essentially, these are the number of hypotheses that you make. And if you are calling something significant at the 0.05, so basically, the moment you have done something like at least close to 70 comparisons, so if you have an assay with 70 compounds, let alone an untargeted assay, basically the probability that you have at least one false positive is 1. So essentially, for sure, the moment you start doing enough comparisons, because you have a lot of metabolites to test, and when you start calling them significant at the level of 0.05, the moment you reach something like 60 of those comparisons, for sure you know that you have false positives. That's a mathematical fact. So in this table, basically, if I'm doing M comparisons, basically I can categorize them, basically whether the underlying hypothesis was true, something that we don't know. This is sort of an oracle, has this access to information, or the alternative, basically whether the mean levels of the compounds across two groups were the same or different. And then what was my decision? So this is what goes on in the underlying hypothesis, and this is what our decision is. And basically, here is sort of the issue, basically the number of false positives. So essentially, when you do this type of multiple tests, you would like to control for false positives. And there are these two concepts. This is an old concept that goes back maybe since hypothesis testing started, almost 100 years. And basically, when you are testing for the family-wise error rate, basically is the probability of at least one false positive. The more newer concept that came about in '95, and it has taken over the literature, especially when you look at omics data, is the false discovery rate, which is the expected proportion. So the two concepts are slightly different because this you control the probability, which is something you control something much more tightly, whereas here you are interested in an expected proportion. And these are sort of the formulas that are not but interesting at the time. So when you basically use this approach of the family-wise error rate, is appropriate when you want to guard against any false positives. So that's why I mentioned that this is a concept that is important when you have a small assay, because you don't have that many metabolites that you are examining, and basically you would like sort of to control for having false positives. On the other hand, when you work with an untargeted platform, first of all, this is going to become, if you're trying to control for this type of concept, is going to become too conservative because you are asking too much. And at the same time, given the fact that you have hundreds or even thousands of features, you can afford to be a little bit less conservative and afford a few false positives. And therefore, that's why in almost all omics studies, essentially you see in the papers people talking about FDR. But on the other hand, for example, if you're doing a very specific and small assay because that's what you're interested in, or you're only interested in a particular metabolic pathway, in that case, you may want to be a bit more conservative and control for that concept. So essentially, what you do is you adjust your p-values. So basically, you get the p-values from your software the usual way, and then you sort of sort them from smallest to largest. But instead of sort of using a fixed cutoff, which is 0.05, and therefore in that case, as we've seen before, that you're going to have false positives, you start sort of adjusting your threshold, and therefore, given the fact that this number, you see, here is the 0.05 that you had regularly, but here you make it much, much smaller by first dividing by the number of hypotheses that you are testing. So if you have 20, this becomes 0.05 over 20, but then you keep adjusting it by the order that you see that particular value. So at the end of the day, by doing this sort of adjustment, essentially it shows that you control the false positives in your collection of your hypothesis at the 0.05 level. So this is sort of a practical, simple procedure, and essentially, it's still conservative, but for small assays, achieves the goal. So therefore, you control your false positives at the appropriate rate. In terms of the false discovery rate, this is what happens when we have hundreds of hypotheses. Again, this is the quantity of interest, because these are the number of false positives that you're going to have based on your decisions. And then you are only interested, instead of controlling the probability, just to control a proportion. And the procedure exactly works in a similar manner. In basically, what you're trying to do is, again, you rank your p-values. But in this case, we have hundreds of those. So think of Tanu's presentation where she had 1,200. So this goes from the smallest to the largest. And basically, you keep calling some of them significant, basically using this type of threshold, which, again, delta is the level that you have decided to call them significant, but then M is the total number of hypotheses, let's say 1,200, and this is the index in this list. So it's much easier to see exactly what goes on with this sort of table. So suppose that I'm looking at the top 10% and I would like to control my false discovery rate at 5%. So these are the raw p-values that come out of the software. Whether I did a t-test or whether I built a much more complicated analysis of variance model, I get this p-value. And here what I'm given the value of delta, the threshold of delta that I decided, I'm calculating this deterministic quantity. So here, since I only have 10 hypotheses, essentially this is delta over 10, and this is 2 delta over 10, and so on and so forth. So essentially, I get these numbers. So, and then the question is, if this number is smaller than this threshold, then you see that this threshold increases in an appropriate manner, in a linear manner. And everything that meets the threshold, I call it significant. Anything that doesn't meet the threshold, I don't call it significant. So in this particular case, what I'm showing you is I just ran the procedure using t-tests, something very basic, the baseline differences between the two groups at the baseline, and PUFA diet for the control subjects. And in this case, I didn't even use t-tests. I used this more fancy permutation test because there were some violations of the normality assumption. This is sort of a detail, but at the end of the day, even this procedure spits out a p-value, an unadjusted p-value. So I have 41 hypotheses in total, and what I'm plotting here is for these unadjusted p-values that came out of this procedure, how they look like. So I'm doing a histogram. So I had about 10 of them that were less than 0.01. I had another 5 that were less than 0.2, and so on and so forth. So then the question is, if I decided to call everything significant below 0.1, so that's what I decided, I would have 10 significant metabolites. But at the same time, would that be true given the fact that I'm doing 41 comparisons and there is this issue about false positives? And how do I control the rate of false positives? So what I'm showing you here is the blue line is the ordered values of my p-values. So there are 41 stars on this blue line, and I start from the smallest p-value, and I go all the way to the largest p-value. So if I were to call anything below 0.1 as significant, I will have these 10 guys, as we saw in the previous table. If I use the more conventional threshold of 0.05, I would still have 5 compounds that I will call significant. However, if I do that and I call this 5 significant, I'm running this risk of having false positives at a much higher rate than I would like to control for. So what I'm showing you here with the red line is if I want to control the false positives at the 5% level, whereas the purple line is if I want to control my false positives at the 10% level. And it's exactly those delta J over M lines that I showed you on the previous table. Of course, here, we don't have that many significant p-values to begin with, even unadjusted p-values. So what I'm doing here is I'm zooming in this little area. And you can see that if I use the 5% level for false discovery, I call significant only 2. If I use the 10%, I only call 3. So you see that especially when I do this type of adjustments, having guarded against the issue of false positives, given the multitude of hypotheses that I'm testing, I'm calling a significantly fewer than the one I would have called if I used a fixed threshold. You see, if everything is significant, or I call significant at a level of 0.05, essentially I'm drawing a straight line. And therefore, this is sort of more liberal and it doesn't have good control. So this is, many of you are aware of this issue. I'm just explaining a little bit of the mechanics and the idea behind, but this is something that you should never ignore. And whenever you see the report provided that has comparisons between, pairwise comparisons between the different groups, or if you do a more sophisticated modeling and you get the results, let's say, from an analysis of variance where you compare more groups at the same time, you always get these p-values. But then you need to do sort of these adjustments, otherwise you will start suffering from false positives, and therefore, your further downstream analysis of what you do with those metabolites may be completely incorrect. And as you can see, you need sort of to calibrate your p-values appropriately. So, for example, in the lipidomics case that Anu showed you, she just presented the unadjusted p-values, and therefore you start getting a much better sense of what is differential once you have started having this, this control. And especially for the untargeted report or for the lipidomics report, given the fact that even after you clean up the features and you say these are the ones that don't have missing data or look good features to me, you're still going to have hundreds of those. And therefore, you need to go into that column in the report on the Excel spreadsheet and then start doing these little calculations before you take those metabolites and start trying to interpret them. Because many of those, if you just stick to a fixed 0.05 level, let's say, many of those are going to be false positives, and you don't really want to use those for anything further as you interpret your data or you're trying to understand biologically what goes on. So when I used these three that passed my test for this particular comparison, this was the one that came up. And basically what I'm showing you here is how nicely sort of the visits separate. Essentially, most of those are at this level, and most of them cluster fairly nicely. I mean, this is not perfect clustering, but basically I get a much cleaner sort of picture. So this is why we use sort of differential analysis to identify which metabolites or features separate nicely our two groups. But unless I have this type of control, essentially I may be looking at, as I've already mentioned, at the data with a lot of false positives that, essentially they're not that informative. And this becomes even more pronounced when you start dealing with other omics data sets where, so you have 20,000 genes or, yes?
When you have these multiple testing, you're assuming there are multiple independent tests.
Yes.
And I assume some of these plates in
Sure.
the dendrogram are not independent.
Yes, very good question.
Do you have such approach?
Okay, so this is a very, very good question. So for this false discovery rate, as long as there is positive dependence between your hypotheses or positive correlations, in the literature there are extensions that come up with more sophisticated type of controls. How to come up with this line. So if you believe that your hypotheses are positively correlated, the answer is yes. And for those of you that may be using our code, this is not really in more commercial software. This is much more recent in the statistical literature. So this FDR procedure that I described, many of you may have heard it as the Benjamini-Hochberg procedure. So if you have positive correlations between your hypotheses, there is an extension due again to Benjamini and Yekuteli, and this is sort of in many of the R packages. On the other hand, if there are positive and negative correlations between your hypotheses, this is an area of active research and there is now no control out there. We don't know exactly what to do, But you pretend that, sort of, these are sort of independent and you take it from there. Probably you know that there are a few more false positives that escape because we don't have a good control, but this is a hard topic and people have been looking at it for the last 10 years and there is no kosher statistical adjustment procedure out there yet. So this is the state of the art. Other questions? So always keep that in mind, and especially when you look at papers and you only see unadjusted p-values, be very, very, very skeptical about the biological findings, because many of them are based on false positives unless you have done some of these control type of procedures. since I have about 20 minutes, and I would like sort of to do an introduction to some of the things that Ale is going to talk about, let me skip this session, the next section that talks about sort of biomarker discovery, and I may come back in the last 15 minutes that I have at 4:15 and give you some flavor. So what I would like to do, I mean, you still have the slides. And I would like to spend a little bit of time talking about pathway enrichment, because this is one way of start integrating omics data. So pathway enrichment came out when people started with, when people wanted to enrich Go terms, gene ontology, and then it became very, very popular in microarray type of studies. And the biological question of interest is whether a set of functionally linked, in this case, compounds or metabolites, is differentially expressed across two conditions. So suppose that we have the control and AFLD samples, or the control samples under the PUFA, the carbohydrate diet, and we would like not to look at one metabolite at a time, all the things that we have been doing up to this point, but we would like sort of to start thinking more from a systems perspective. And given the fact that, for example, you can look at the pathways in KEGG, you have that information to start creating your functionally linked compounds. Ala, that follows me in terms of presentation, she's going to show you tools that have been developed both here and in the literature, you know, how to sort of to semi-automate that. What I would like to do in the next 20 minutes is sort of walk you a little bit to walk you through the main ideas of exactly what these techniques that you can find in the software do. This is a great paper in PLOS Computational Biology. It's 3 years old. Essentially, you know, this business started at around the turn of the century, and it talks about 10 years of pathway analysis, and basically it uses this categorization, 3 generations of pathway enrichment methods. The first one essentially was inspired by all the things that went in Go analysis, and then the second generation of methods was motivated by microarray analysis, and the latest class of methods that is still under development in an active research area tries essentially to incorporate network information, for example, in the metabolic, for metabolites, reactome type of information, in order sort of to improve the results. So let me walk you through the 3 methods. So the overrepresentation analysis has a very, very simple context. So first of all, you need to define a list of metabolites. So let's say that you are looking at the amino sugar pathway. So that's the list of metabolites that you have mapped to that pathway. So Ala is going to, in her presentation, talk about how you do the mappings and what tools there are out there. And given the fact that you have a certain number in your list, you need to decide, that's your second decision, of which of them are differentially expressed. And given the fact that potentially you make all these comparisons, you need sort of to have the appropriate false discovery rate control that we just discussed. And then you have an alternative set, all the metabolites that are not in the pathway. So this is your complement. So these are the members in the pathway. Some of them pass your FDR threshold, so there is this cell, and some of them are not differentially expressed, so they fall into this cell. And then all the other metabolites that you have seen, and again, you can categorize them as differentially expressed according to your FDR threshold, or non-differentially expressed. So essentially, you have this 2x2 table, and this was exactly the idea when people start thinking about this type of tables with Go terms, whether some of the genes belong to the particular Go term under consideration, or they didn't belong. So essentially, it's the same idea, but right now we just translate them to metabolic pathways. And basically, the question that you're asking is whether those that are differentially expressed and in pathway are overrepresented. And the underlying test is either a chi-square test or Fisher's exact test that you can look up. There is a very nice explanation sort of in Wikipedia. The other thing that you're doing, given the fact that in principle, based on either your untargeted or targeted data, you may have lots of pathways. Again, at the pathway level, when you start running this type of procedure, you are doing, again, a lot of hypotheses. So again, you need sort of to control for multiple comparison. So you see how important the concept of multiple comparison is. And in this particular case, you have control for multiple comparisons of what you call differential or non-differential within the pathway. And given the fact that you do this procedure for a number of pathways, again, you need to control for multiple comparisons. So this is very simple and computationally inexpensive, given the fact that these tests are very easy to run and they are programmed in many software packages. So the pros is that it's computationally fast, and the other thing is that whatever exact test you use, so essentially which procedure you used in order to call a particular compound differential express, whether it was a t-test or a more robust version of the t-test or a permutation test, the results are fairly robust. So that means that, as long as you have a reasonable choice there, you can carry out the procedure. It's implemented in many platforms. All open source tools essentially have it, and also commercial ones. For example, Ingenuity Pathway Analysis, that's exactly what they use. However, that's why in the review paper it's called the first generation of pathway enrichment methods. It has a number of cons. One of the things is that all compounds are treated equally. So since the approach only utilizes binary information, what do I mean by binary information? At some point, you make this distinction, you set a fixed threshold, yes, maybe FDR corrected, but either you call it differential or non-differential. The fact that some of the compounds in the pathway may have been super differential, exhibiting very, very small p-values, whereas some others were borderline differential, the procedure is oblivious to that information. And again, you may say, why does this matter? Well, if I was doing this with genes where I have very large membership of pathways, if you take some of the signaling pathways, they have 100 members, 150 members, this may not be such a big issue, but given the incomplete coverage of biochemical pathways that we have, both from target and untargeted platforms, this is something that, leaves information on the table and doesn't fully utilize the information. The other thing is that, again, the threshold that you use in order to decide what goes into the different cells makes the procedure in some time giving slightly different results in the following sense. If I use the threshold here, let's say at 5%, I get some entries in this cell, some entries in these cells, and so forth. Why 5%? I may decide that I want to do it at 7%. And therefore, this starts changing quite a bit. And together with the previous issue that doesn't take into consideration that some of the compounds may have been very strongly differentially expressed, it doesn't make the procedure very robust. And again, this wouldn't have been such a big issue if my pathways had very large memberships, which is the case for genes. So this is sort of a second disadvantage of this type of procedures. The other thing is that it ignores correlations among the compounds, the question that you just asked. Ignores overlaps between pathways. There are some compounds that are mapped to multiple pathways, and therefore this procedure, again, ignores that information. And finally, can only handle comparisons between two conditions. Of course, some of these criticisms may be a little bit too harsh because most of the procedures that we have these issues, but the first two are very specific of exactly how this procedure is set up. Because you need to have the threshold, and all compounds are treated equally. So a few comments. What about the correlations between metabolites? Essentially, the same is going to sort of happen between lipids from the lipidomics platform. You're going to have fairly strong correlations within the classes, and also pathway overlaps. Especially the pathway overlaps, namely that given the fact that the same metabolite may be mapped to multiple pathways, essentially it's going to start inducing positive correlations. And this is exactly what I mentioned 3 minutes ago. As long as you have positive dependence in terms of the classical procedure of Benjamini-Hochberg for controlling force discovery rate, there are extensions by Benjamini-Yekuteli. And if you don't want to control force discovery rate, but you want to control the family-wide zero rate, which is a much more conservative procedure, again, there is work in the literature to address this issue. So the pathway overlap, by being a little bit more sophisticated downstream of how you do your FDR corrections when you test multiple pathways, essentially can be handled. But the first issue, these first two issues sort of limit the applicability, but essentially there are better procedures. And this gets us to the second generation of functional class scoring approaches. Many of you, I mean, this is kind of a fancy name that the authors of the review paper came up with, and most of you have seen the words GSEA, Gene Set Enrichment Analysis, that came out of the Broad in the PNAS paper of 2005. So essentially, this was the first approach that used this type of idea, and since then the literature has a lot of variants, tweaking the results, getting better statistical power, and so forth. So if you read this paper, which is, it's sort of opened to this new generation of enrichment analysis techniques, here is the basic premise of all these approaches. It says that you may not have very strong differentials when you do the comparisons, but you may have lots of them. And this is sort of the idea that you may have coordinated coordinate changes in sets of functionally related compounds, essentially in your biochemical pathway. So why did the people at the Broad come up with this idea? Of course, they were talking about genes, but if we look at this sort of little table, suppose that you were in this particular setting. Suppose that we pick a threshold of 5%. And all your compounds are differentially expressed and they have p-values of, let's say, 7%. That means that this cell is going to be 0 and this procedure is going to say the pathway is not doing anything. But on the other hand, all the members of the pathway, when you look at the data, may be differentially expressed, but they may not meet your threshold. Yes, of course, somebody will say, okay, increase the threshold, but then we start sort of playing this game, how many thresholds to pick and stuff like that. So this was the issue that the Broad Institute, the original idea, they were trying sort of to overcome. And their basic premise was that you may have lots of not very strong differentially compounds, or genes in that case, but all of them may act in unison. And therefore, as I've already mentioned, such changes would most likely be missed by the overrepresentation analysis unless you open the threshold too much. So what are the mechanics, exactly how these procedures work? And there are lots of variants, and again, you need sort of to read the fine print in order to see exactly which implementation is in the piece of software that you use. So pick a test statistic or a compound level statistic. You can pick the t-statistic. If you believe that your data are normal, you can pick a z-score. There are procedures that even take the fold change or the log fold change that is available in the report. So you need to make that decision, and there are lots of choices. And then you compute a pathway enrichment score that basically takes either a sum or a weighted sum of these compound level statistics. So let's say that we have a pathway with 10 members. We do t-tests, and therefore we have t-test statistics, not the p-values, the test statistic itself. Or we have the fold changes between the two conditions, and therefore we have these 10 numbers. And then you compute this enrichment score where essentially you sum those up. And or you take their mean, or you take the median, or you take, you first rank them in terms of which is the smallest and the largest, and then you take the rank, and so on and so forth. Again, there is lots of variance out in the literature. But the issue, the key idea is that you start with the compound level statistics, and then somehow you aggregate them by averaging them, or summing them, or normalizing them in a different way. And then you have your score. Then the tricky part is, suppose that I get a score of 5 after I did this exercise. The question is this 5 large or small? I have no clue. Is a 3 large or small? So here is where the idea of permutation procedures that I talked before the lunch come into play. Because essentially you find the sampling distribution, essentially, you know, what are the possible values that this score that you derived can take, and whether the observed score is extreme compared to the other values that this score can take if there was no enrichment of the pathway, and then do this comparison. So essentially, that's the idea of the permutation procedure. That's something that you can easily run on the computer, and basically you derive computationally the underlying sampling distribution, and then for the value that you got from the actual data, let's say 5, you see within this sampling distribution whether it's extreme or not. And that gives you the p-value for your specific pathway enrichment score. So you see where the idea of permutation procedures comes so handy, especially when you start calculating complicated statistics. Here, for the t-statistic, as I mentioned before lunch, we know exactly, we can go into the tables in the book and find out what is significant, what is not significant. But here, for these complicated pathway enrichment scores, and especially if you take the means, the medians, and so forth, we don't know that, and therefore we need to rely on this idea of the permutation procedure. For example, if we go back to the example that Anu talked about, where there were only 3 replicates for the cell lines, probably using a t-statistic is not a very good idea with 3 replicates. In that case, maybe you need to use a rank sum test or some more robust statistic before you trying to calculate the pathway enrichment score. And people have done a lot of numerical work, even simulation studies, and this is sort of what we have learned over the years by doing this type of comparisons. What are the pros? Essentially, it overcomes the limitations of a representation analysis because it takes into consideration how strong the changes were. Because it looks at the statistic itself. It doesn't use a threshold and say differentially expressed or non-differentially expressed as a 0, 1, but looks at the exact value of the t-statistic, and therefore, different compounds bring different amount of evidence when you calculate the pathway enrichment score. Therefore, you don't use arbitrary thresholds, and so forth. The bottleneck is, of course, this permutation step, because in order to get the sampling distribution, you need to run this procedure 2, 3, 4, 5,000 times in order to have a good calibration of the significance of your permutation score. 10 years ago, these were important issues. These days, probably you can even run it on your smartphone. Again, it ignores overlaps between the pathways, but we have discussed this issue before. Overlaps between pathways induce positive dependence, and therefore when you do the adjustment for all the pathways that you have tested, you just need to be a bit more sophisticated of how you control the p-values from your multiple comparisons. Some variants ignore the magnitude of the measured changes, others do not. So again, there are lots of choices in the literature. And this is sort of a general criticism that, for example, if you have 3 conditions, benign cell lines, androgen-dependent cell lines, androgen-dependent cell lines, and you would like sort of to do everything together, you cannot. You need to break them into pairwise comparisons, but this is something that essentially that's the state of the art. So the last thing that I will not give you any details is pathway topology approaches. So suppose that we had the underlying network map. So we knew how the compounds were related. We have reactome information that we can extract from KEGG, and so forth. So this is the 3rd generation, and this is still a very active research area. So the main characteristics is to try to incorporate interactions between the compounds. So again, as you can see,